This is MohammadAmin Atashi, a graduate research assistant at the Department of Electrical and Computer Engineering under supervision of Dr. Arash Mohammadi at Concordia University. And my thesis is entitled Multiple Model-Based Indoor Localization via Bluetooth Low Energy and Inertial Measurement Unit Sensors. Starting by a brief introduction on IoT concepts and the applications of indoor localization in this context, my presentation will focus on three main indoor positioning frameworks known as Bluetooth Low Energy, Inertial Measurement Unit, and Pattern Recognition-based indoor localization. Finally, I will present a brief conclusion and some implications and directions for future work. Let me start by providing an interesting trend in IoT. Starting from more than 15 billion in 2015, the number of interconnected devices has been doubled in 2020 and is expected to increase to more than 75 billion in 2025. The applications are manifold in different contexts, such as smart homes, smart cities, navigation, and so on. In fact, after the emergence of advanced artificial networks and efficient computational powers, cloud networks, the IoT concept has even further empowered. Location, either the indoor or the outdoor one, is considered as one of the most important parameters in IoT concept. Although there have been many outdoor localization frameworks, such as Global Positioning System, Wi-Fi, that accurately locate a user in an outdoor venue, there is lack of accuracy in indoor positioning frameworks. The current frameworks are mainly based on the Bluetooth Low Energy, inertial measurement units, ultra wideband, Wi-Fi, ultrasound, and so on. In this presentation, my main focus will be on the first two technologies, Bluetooth Low Energy and Inertial Measurement Unit. Then I will propose some multiple models that use the fusion of these two technologies. The applications of localization can be categorized in two main groups: location-based services, in which the exact location of the user is desired, and then the proximity-based services, in which the profiling and heat map of the activities performed by the user is the subject of indoor localization. In fact, starting by the first localization technology, which is Bluetooth Low Energy, referred to as Bluetooth Smart, they use the small wireless sensors known as beacons to propagate data. This BLE packet consists received signal strength indicator, RSSI, that depends on the distance between the device and the beacon. As you can see in this pathless model, the RSSI value can be related to the distance between the device and the beacon. You can see the BLE advertising channel starts from 2.4 gigahertz to 2.48 gigahertz. And the important thing is that the BLE channels are very narrow banded. So there is a risk of interference in Bluetooth Low Energy network. Also, there are some overlaps between Wi-Fi network and Bluetooth network, which will increase the risk of interference and noise in our framework. Moving to the second indoor positioning technology, which is inertial measurement units. This framework uses accelerometer, gyroscope, and magnetometer to report the bodily acceleration, angular acceleration, and magnetic field in the venue. In fact, although these sensors seem to be very attractive at the first sight, but they are prone to drastic fluctuations, random drifts, and hard and soft iron effects. I will elaborate on the hard and soft iron effect in the next slides. The most popular IMU-based indoor positioning framework is known as pedestrian dead reckoning, which iteratively attempts to find the location of the user in an indoor venue by applying two heading estimation and step detection algorithms. The third and more recent indoor positioning framework is called pattern recognition, which tries to extract, learn, and then predict the labels for different action units, actions, or tasks performed by the user in an indoor environment. For example, left turn, right turn, short step, long step, and many other movement states and action units are predicted based on two action unit classification. The first one is action unit classification, and the second one is movement state. In most of the cases, LSTM is applied for being able to be trained on multivariate data. Here you can see that the segments are different, have different lengths and are multivariate. Therefore, LSTM architecture can be represented here. It would be applied on the and be trained on the IMU data. Therefore, to have an overview on this thesis, my presentation will focus on three main indoor positioning frameworks: BLE-based, IMU-assisted, and pattern recognition-based. In each domain, I'll propose a multiple model that can boost the accuracy of indoor positioning and would promise a near real-time localization framework known as RTLS. Starting with the first domain, which is Bluetooth Low Energy-based indoor localization, and the first step is to collect the RSSI values propagated from the BLE sensors. And here you can see that the RSSI values are prone to multipath and fading effects. Therefore, these effects will result in drastic fluctuations of the RSSI value. As you can see, the Kalman filter can smooth the drastic fluctuations in the RSSI value to mitigate the randomness of indoor positioning, localization estimation. And the two underlying location estimation methods for BLE-based context is known as path loss model and fingerprinting model. While the first one, path loss model, tries to estimate the location of the user based on the distance of the user's phone or the device to each BLE beacon, as you can see in this figure. However, the fingerprinting model would try to construct the RSSI map at first in the offline phase, and in the online phase, while the user go through the path trajectory, the framework wants to find the highest similarity metric between the zone in which the user is standing in and the trained RSSI values. Apart from the drastic fluctuations in the RSSI value, there are other parameters that negatively influence indoor localization. As an example, the instinct differences of sensors would result in low accuracy. For example, as you can see here, the purple sensor has highest mean value of the RSI values in the fixed distance and fixed orientation. And some other sensors have higher variation. These randomness would result in inaccuracy. Also, as I experimented the orientation effect on the RSI value, uh, I showed that for a particular sensor, for a fixed distance and different orientations, the RSSI value levels vary a lot. Therefore, as you can see in this figure, the level of orientations and also the fluctuations vary based on the orientation of the smart device. To even more investigate the profound effect of orientation and handling gestures on RSSI value, you can see that I have investigated 2D and 3D orientation effects on the RSI value, starting from 0° to 350 for 8 different orientations. The average RSI value has reported in this figure. And as you can see, the level of average RSI value varies a lot. The same trend can be seen here for 3D orientation. From -90° to 90°, the amount of average, the average RSSI value varies a lot, which will put our model into the risk of inaccurate location estimation. Also, the other parameters affecting RSI value, such as line of sight, non-line of sight effect on the RSI value, and effect of obstacle on RSI value, has been investigated in my experiments. On the second floor of Concordia building, I investigated the LOS and NLOS signal propagation. Well, you can see that there are different characteristics. The NLOS and LOS signal propagation achieves different levels of fluctuations and mean RSI value, as you can see in these two figures. And also by having a wooden wall between the transmitter and receiver of BLE beacon, I showed that there is a huge difference of RSSI values with obstacle and without obstacle. In order to resolve those challenges and micro-locate a user in an indoor environment, I proposed a multiple model multiple model which is consists of KNN fingerprinting module and particle filter module. The first module is consists of two phases. In the offline phase, the RSSI map of the indoor venue is collected. The RSSI values at each zone are collected and the Kalman filter is applied on the RSSI values, while in the online phase, where the user goes through the path trajectory, the zone in which the user is standing in can be determined uh, by detecting the highest accuracy metric of the um, of the particular zone. For example, here, the output of the classification can be the central point of this square in which the user is standing in. And in order to find the accurate location of the user inside that square, the particle filter would determines the accurate location of the in the predicted zone by distributing these particles, and by weighted averaging on the coordinates of these particles, the accurate micro location of the user can be achieved. To implement a real-world scenario and evaluate the accuracy of my proposed model, I designed a 2-meter to 4-meter environment, which resembles a corridor environment. And this environment is divided into 32 zones. Each zone has 50 centimeter to 50 centimeter width. So the total 200 RSSI values for each zone is collected, and then the Kalman filter is applied on the raw RSSI value in order to mitigate the fluctuations. In the online phase, the user would go through the path trajectory, and the exact location of the user is targeted in this framework. As you can see in this figure, by having 100 of particles, the mean square error for the proposed framework was 95 centimeters. And as an expected trend, when we increase the number of particles, the MSE would decrease. Moving to the second indoor positioning technology, which is inertial measurement unit sensor. The first step is to collect the IMU values from accelerometer, magnetometer, and the gyroscope. Therefore, we developed an application based on iOS platform to collect the IMU data. While it's collected, we can apply the PDR algorithm, which is the most popular and widely used framework in this context, by applying the pre-processing unit, heading estimation, and the step detection. The pre-processing unit is consists of moving average filter and ellipsoid feed calibration unit. The moving average filter would cancel out the high frequency noise in the IMU data, while the ellipsoid feed calibration is designed for magnetometers, hard and soft iron effects. These effects are generated by presence of temporary and permanent magnetic field in the venue, which will distort the values reported by the magnetometer. As you can see in this figure, the red dots are representing the magnetometer's x-axis, y-axis, and z-axis, which are distorted data. So in order to make it calibrated, we will map these data on the ellipsoid surface, centering at 0, 0, and 0. Therefore, by doing this, we can mitigate the effect of hard and soft iron effects of the magnetometer to yield a better heading estimation unit. The heading of the user's phone can be determined by yaw angle. In fact, if the user's phone is placed in the 2D plenary surface, the yaw angle represents the orientation of the user's phone. Here you can see the pitch, roll, and yaw angles. In order to determine the yaw angle, first we should define pitch and roll angles based on the accelerometer's data. By manipulating magnetometer's data, we can yield yaw angle representing the heading of the device. The third module is the step detection in the PDR algorithm that tries to find the global peaks in the IMU signal. As you can see, the inertial measurement unit has a periodic trend. And here, if we want to count the steps and find the indexes of the steps, we can count the global peaks in the IMU data by setting a threshold for IMU data. This shows a real experiment for a real demo that I did in the second floor of Concordia University, where I had a path trajectory of a square-shaped path trajectory, and I went through the path trajectory while holding the user and the phone in my hand. As you can see, the predicted path trajectory for my uh, actions were like this figure. And as you can see, the last section of the square is error prone because of the heading estimation. Therefore, this is not like the accurate indoor positioning framework. And by considering 2D floor map, which is known as map considered PDR, we can improve the accuracy of indoor positioning. Let's see this path trajectory, and the PDR algorithm could localize a user and estimate the path trajectory like this. However, as we see, this path trajectory is error prone. In order to correct the erroneous estimates, we can apply the map and knowledge. By map, I mean the exact location, the exact coordinates of the walls, obstacles in the indoor environment. And as you can see in this figure, the localization achieved higher accuracy, and it's more accurate than the PDR algorithm. Here is the heat map generated by the map considered PDR. Also, in another attempt, the cumulative error effect is more conspicuous in larger scale maps. Starting from a start point here in the ninth floor of Concordia University, I wanted to go through a path trajectory to go to Dr. Ara's office. Therefore, I went through this path trajectory. The estimated path with PDR algorithm is like this, which is not accurate. As you can see, it goes through the walls and it doesn't abide the rules of map. Therefore, we add the knowledge of the map and we define some thresholds for X and Y axes. As you can see in this map considered PDR, the better accuracy have been achieved. However, having the knowledge of exact location of the obstacles and walls in an indoor venue is really time consuming. Also, the initial position of the user is considered as is strictly required. If the user starts from somewhere here, then the localization would be distorted. Therefore, uh, just a standalone IMU-based indoor positioning frameworks are not a viable approach. By having the fusion center that receives the RSSI values as well as the IMU headings at the same time and fuses these data, and feed them to KNN, SVM, and ANN classifiers, we can determine the orientation of the user's phone. This will mitigate the effect of orientation that I elaborated in the last few slides. And by defining and optimizing the path loss exponents for each orientation, we can increase the accuracy of indoor localization. In the conventional methods, the N and C0, which are the path loss exponents, were just fixed at the first step. But in our method, we would classify the orientations, the user's orientation, and based on that, we will optimize these parameters. Therefore, in this section, I proposed three main methodologies: RSSI only, IMU-based, and fusion model, in which in the RSSI only model, I would consider the RSSI vector received from beacons as the input to the classifier for having the orientation. IMU-based would provide the yaw angle, and fusion model would merge these RSSI values and the yaw angle, which is predicted by the inertial measurement units, and would fuse them, would feed them to the KNN, SVM, and ANN classifiers to have the orientation. And for the RSSI solution, as you saw here, the standalone scenario and multi-sensor scenario are designed that I elaborate on them here in this slide. The standalone orientation prediction is designed in a way that each BLE would determine the distance of the device by itself separately, and then based on weighted averaging, the final distance is achieved. However, in multi-sensor orientation prediction, the vector consisting the RSSI values of all 4 beacons are fed to the classifier to find the orientation, and based on that, we will define and optimize the path loss exponents. The left-hand side table here shows the higher accuracy of the fusion model compared to the standalone solutions. However, for the standalone solution, KNN with K equal to 5 achieved a higher accuracy than the other 2 classifiers. Moving to the third and more recent indoor positioning framework, which is pattern recognition based indoor localization. This method would input the IMU data to 2 classifiers: action unit classification and movement classification. The labels, the output labels are shown here. By extracting, learning, and predicting the actions performed by the user, for example, left turn, right turn, normal step, short step, we can predict the location of the user in an indoor environment. Here you can see the figure of the conventional model. 2 LSTMs are trained and then would try to predict the labels for different multivariate action units, as you can see here. There are some disadvantages and challenges regarding this conventional model. As you can see, starting from 20 to 60, approximately 14 number of tensors are generated in order to just find the prediction label for one action unit. This is really time consuming. And this trend will goes on for other action units. And this implementation would not result in RTLS, real-time localization service. So I ended up with some innovative ideas to reduce these high computation of tensors and reduce the computation requirement in order to achieve near real-time localization system. The other contribution is that in the conventional models, just stop walking and running modes were defined for movement states. However, in an indoor environment, maybe the user wants to go upstairs and downstairs. The conventional model cannot deal with those types of data. Therefore, in order to overcome the challenges that I mentioned, 3 online dynamic windows are proposed: signal processing based, NLP inspired, and the fusion model. In the signal processing based, the goal is to mitigate the excessive runtime. NLP1 tries to improve the accuracy of the signal processing one, and the fusion model targets the NLP fusion model wants to end up with a trade-off between the accuracy of NLP-inspired online dynamic window and the signal processing online dynamic window. Therefore, this fusion model would render near real-time localization service. As you can see in this figure, regarding the first contribution, which is the signal processing-based dynamic window, despite the conventional model that it generates numerous segments and will feed numerous segments to the LSTM classifier to just find one label of the predictions, in my proposed model, a signal processing approach is implemented. By defining 0 cross points, we can segment and we can find the start and end point of each action unit. And there is no requirement for tensor calculation, although the accuracy would be a bit less than the conventional model, but it would render near real-time localization service. The 0 cross points are defined based on the following rules. For example, the 0 cross point should be between 2 consecutive points, and just only one 0 cross point should be between consecutive points, peaks, I mean. And the energy of the 0 cross points should be between these thresholds, which would promise a minimum energy for these 0 cross points, because they are the start and end of the action unit. So they should have the minimum energy as possible. Moving forward to the natural language processing inspired dynamic window, which uses the tokenization approach in the signal processing in the IMU data. we can see the conspicuous similarities between the text data and IMU data, since they are both sequential and they have some sub actions. For example, here in the statement, in the sentence, the tokens are sub statements, which are the words. And by concatenating these words, a statement is created. Then the statement can be classified as, for example, this sentence to be sarcastic or not. The same here, I became with an innovative idea to find the start and end points of each action unit by defining some sub actions. As you can see here, these tokens are sub actions, and by concatenating these tokens, we can end up with a meaningful pattern in IMU data. Once we defined a meaningful pattern, then the label of that pattern, for example, short step, normal step, left turn, right turn, can be predicted. Here is an example of NLP-inspired dynamic window. For example, for the short step, three tokens were used, while the normal step used 4 tokens. This work has never been used in the literature, but uh, the accuracy of this proposed model proves to be very high. Here you can see the comparison between the average running delay and the accuracy of signal processing and NLP-inspired dynamic window. Although the traditional dynamic window achieved higher accuracy, but there is an excessive delay for each action prediction. Actually, it is the dynamic window is implemented in an offline manner. It's not online. But however, in our proposed models, the dynamic windows are online and the excessive delay is mitigated. The advantage of signal processing is the very low uh, delay, and the advantage of NLP one is that it gained higher accuracy than the signal processing model. In order to implement a trade-off between the average delay time and the accuracy of two proposed models, I ended up with a fusion dynamic window, SP-NLP fusion dynamic window, which is consists of 2 steps. First, the signal processing dynamic window tries to find and segment the action units, find the start and end point of each action unit by defining the zero cross points. So there is no need for tensor calculation. If the accuracy of this zero cross point splitted action unit is not that high and does not exceed the predefined threshold, then the NLP model would come in and would generate some segments in the vicinity of this zero cross point. This would render higher accuracy of location estimation for our proposed model. Therefore, by applying this algorithm, we can achieve a near real-time localization system. To implement and evaluate the performance of the proposed dynamic windows, I have designed these scenarios, which consist of several stairs, and the path trajectories are shown here. The users can go through a path trajectory with actions by their choice. For example, they can run, walk a little bit, and uh, by empirically by the cameras that are installed in the venue, the labels for the training data would be empirically collected. Here you can see the labels for the first LSTM and second LSTM. The first one uh, would classify the movement states in which these two movement states are added than the conventional model. And here the different action units are shown. The LSTMs could be trained on this data, and the classification accuracy of the proposed model would be shown in these figures. The confusion metrics for movement states, the upper score confusion matrices, and the bottom confusion matrices show the action unit confusion for these proposed models. As you can see, the accuracy of the fusion model is somewhere between the NLP and signal processing one, while the runtime speed compared to the NLP one is much higher. In fact, in order to have a brief overview on the thesis and have a conclusion, I can mention that based on the conventional fingerprinting, pedestrian dead reckoning, and pattern recognition models, I found that there are some disadvantages and challenges regarding these frameworks, such as the RSSI fluctuations, effects of different parameters on the RSSI value. For the PDR1, I found that there is a high error in step and heading estimation. And the worst thing is that the error is cumulative error. For each step, it's added. The error will be added for the next steps. And for the pattern recognition one, uh, the conventional models were not RTLS, real-time localization services, and they required high tensor computations. To tackle those problems and bring contribution, I proposed three different multiple model frameworks. That in the first model, I combined the particle filter with KNN to micro-locate the user in an indoor environment. In the second one, I proposed the orientation detection that I optimized the path loss exponents based on the orientations of the user's device to mitigate the effect of orientation on RSSI value. And in the third model, I uh, targeted achieving a near real-time localization service and mitigate the speed and mitigate the runtime delay in the conventional models. These work have been published in uh, conferences that you can see here. And the directions for future work would be uh, implementation of RSSI IMU fusion model in order to consider both the patterns in the RSSI and IMU model. In my presentation, I just focused on the patterns of the IMU signal in order to classify the actions performed by the user. However, the direction for future can be fusing the RSSI patterns and IMU patterns at the same time and evaluating the patterns inside the BLE and IMU based signals. This method would promise a scalable, efficient, and accurate framework, localization framework. Another approach can be to implement a model that considers the lightning and barometer sensors of the user's device, as barometer can give us the height of the device. Therefore, we can have the 3D, instead of 2D, we can have a 3D indoor localization. And also the high time domain resolution based on ultra wideband technology can be implemented. As you may know, the ultra wideband sensors have been implemented in iPhone 12 and Samsung Note 20. Therefore, by implementing ultra wideband technology, one can implement a much accurate indoor localization and achieve higher accuracy. In fact, by applying time difference of arrival, time of flight, two-way ranging, and the ultra-wideband approaches to find the location of the user, one can implement a hybrid model based on the BLE and ultra-wideband to find the more accurate location of the user. Here are some references for your consideration, and thank you for your attention.